So thank you for joining me on this lunchtime. I'll keep it quick because I have to, it's 20 minutes, and then we can all go and get something to eat. So I'm going to talk briefly about some of the decisions and trade-offs made around choosing a non-relational database. And yeah, so a lot of the time when we're looking at non-relational databases, there are often the two things that tend to tempt us that way. One is the promise of speed, and the other is a promise of scale. And when I talk about scale, I also mean things like uptime and so on. But query is obviously something we don't want to forget about as we're developing applications. So the question is, as the NoSQL movement grows and moves on and becomes more mature, can we get all three things from NoSQL databases? This is the project management triangle. Basically, you can have something that's good and fast, but it won't be cheap. You can have something that's good and cheap, but it won't be fast. You can have something that's cheap and fast, but it won't be good. And in data storage terms, perhaps there's something similar. Perhaps there's a data storage triangle of speed, scale, and query. And very often, if you go for speed, then you have to trade off query because you're getting the speed by simplifying the data model or something like that. And if you want to get big scale, then you might maybe have to trade off on speed because the way that you achieve scale is by having multiple copies with lots of possible divergences and so on that need to be resolved, and that slows things down. But actually, obviously, when you think about it a bit more, there's more than just three concerns. There's more than three things to think about when looking at the trade-offs of a data store. There's distributability of the data. There's consistency of the data. There's accuracy, which is different from consistency because it can be wrong and consistent, or it can be right and inconsistent, or inconsistently correct. Yeah, so it becomes more of a star. And then you can't really talk about distributability without availability. And then you think about flexibility of data model, about the ease of use of the SDKs, about how much it's going to cost you to run the thing, and so on. So it becomes actually a multi-sided polygon that just looks like a circle, really. So clearly there are lots of things to bear in mind. So let's try and drill down on one or two of them, or three, in fact. So first up, data models. In the NoSQL world, there are many, many different types of data model. And the one thing that they all have in common is that they're non-relational. But probably over the past 10 years or so, there's been 4 predominant NoSQL non-relational data models. Starting off at the very beginning, obviously key value, nothing particularly complex about that. You have a key and you have a value, and the key could be anything. It has to be something you can reproduce later on. So deterministic data is good, like a user's a login name or something like that could be a good one for retrieving their user profile. But yeah, you can have anything in the value. It could be a string, could be JSON data, could be a binary. It doesn't really matter. The defining thing is that to the data store, the data that you're storing is opaque. It doesn't have any insight into it. It can't help you really query inside that data. It stores it and it retrieves it when you ask for it back. And like I say, you have to have the key. So you have to have a way of rebuilding those keys when you come to need them again. Similar to key value in that you have these aggregates of data in the value side of things, are document databases. So the key differentiator here is that a document database will store some form of known format, so JSON, XML, whatever, and then allow you to index and query the contents of that document that you're storing. So you could you could index the names of all the people in user profile documents and the team that they're in or the place they live or whatever. And then that allows you to do more interesting query rather than just, hey, I have the key, now give me the thing associated with the key. And so then we're getting into a realm where we're optimizing for query, and that data model does that for us. Optimizing further for a specific type of query is column stores, so things like Cassandra and HBase. And here you have a data model that is almost dictating the way that you query the data. So in a similar set of terminology to our familiar relational databases, we end up with rows and columns and things like that. But actually, they're somewhat different. So a row is almost like a key. So here we have an author, and then we have values associated with that, which are in columns, which you append on to the end. So you can have very, very, very wide rows in these column stores with multiple columns added on. So for example, if you're doing time series data, you're storing the output from a thermostat or some kind of repeated report of data every 30 seconds or whatever, then you just throw on another column. And so it allows you to very quickly write out lots and lots of data. But like I say, the data model here actually dictates the way that you query it, because you have to think in advance of the ways that you're going to query it. And then when you have made that decision, that dictates how it's stored on disk. So here we have a bit of a silly example. We have an author, so that's our key family, that's our route into the data, and then we have different books associated with that author. And you can see that I've ordered them by year of release, and this is significant because now if I tell, for example, Cassandra that I want to store those books in year of release, then it will store them on disk in that order, and that makes it great for doing queries that rely on the year of release ordering. So if I want to find all the books from a particular time or between two dates, that's something that's very, very quick to run on that. But again, there's the data model that's dictating to us how we do query. And then perhaps the ultimate example of the data model informing how we query the data is the graph database. There's Euler, who came up with graph theory, and you've probably at least heard of Neo4j. If not, go and try it out. So Neo4j is another graph database, concentrates on not necessarily the value associated with the thing that you're storing, but the way that they relate to one another. So here we have a bit of a silly example again. We have a guitar, we have the band Queen, and we have Brian May. And we can see that there are relationships from guitar to Brian May and guitar to Queen. And they're directional. But we can also have them going in the other direction as well. So we end up with these multi-direction things. So Brian May is in Queen, but Queen has a founder called Brian May. And then, perhaps most interestingly, we can associate type with those relationships. So we could then say, give me all of the bands that have where Brian May played guitar, and you probably get 3 results back. And you can follow that data through. And for more real world examples, this is something you would use for fraud detection. So you might look through someone's previous history of transactions and be able to tell, well, this one doesn't match their pattern. You could say, give me all of the transactions that are outside a particular time, outside a particular location, and then you could navigate that graph and come back with the ones that look a bit odd. So data model is our first consideration in determining whether we're going to favor speed, scale, or query. And yep, relational is still very much an option there. If you have relational data and you really want great query on that, and you're happy to perhaps either deal with the interesting scaling situations you might have there, or your data is fine on one server, then relational is probably the right choice for you. But if you have these other problems of scale and speed, then that go beyond what a relational database can do comfortably or affordably, then maybe you want to look at these other data models. So if data model has an impact, then how does architecture impact the trade-offs that we make? So traditional, master-slave is something we're all familiar with. Clearly, that's going to have some impact on what we do. So, reads would be very fast in this particular situation because we have many slaves that we can read from. Writes might be a bit slower because we have a single master in this particular case. And query is going to be dictated by the data model, but you might end up with perhaps some eventual consistency here. So you might end up with query that is perhaps not less reliable, but something where you can't always consider the results back as a source of truth. You have to be prepared to resolve conflicts. And then master topologies are the other big area that you'll see mostly in non-relational databases. So if you've read the Dynamo paper from Amazon or you've looked at the Google Big Table paper, then you'll see the massa topology described. And there are two variants of massa clustering. One is replicated set topology like this, where you have effectively the same data set on every node, and they replicate changes between each other as they come in. So you can write to and read from any of these masters, and they will replicate the changes. But again, you have this issue of eventual consistency. So you might hit one server to write to it, and then someone else will look for the same document or key value pair or whatever on another server before it's had a chance to replicate over. And so they'll get slightly stale data. And then the other variant of the massa topology is the distributed topology, where you split the data amongst a whole big range of nodes. So you don't copy the entire data set from one server to another, but instead you have something like a hash space, and then you divide up that hash space amongst different servers in the cluster, and they all take their little part of the data set. And you might have replicas, but there'll be replicas of individual documents or key value pairs. So how do they differ? The implications are really that with a replicated topology, yes, you end up having the entire data set on one machine, but probably more interesting is that you have to go for eventual consistency. Whereas in the distributed world, you could have a fully strongly consistent data set across all those nodes, or you might have to have something where you favor availability over consistency. So Cassandra, again, is an example of a database where you are using this distributed topology, but they're favoring consistency because, availability, because they will allow you to write into multiple copies of the data. Whereas in a more strongly consistent configuration like Couchbase would offer, then you only ever write into one copy of it. But then you're trading off availability, because if that one copy goes away, then it's gone away. You don't have multiple master copies of that to write into. So architecture is that second consideration that we have then in terms of whether it's going to give us, whether we're going to get speed, scale, or query, or two, or maybe three of them. So let's have a quick look at some examples of how that affects. So if you imagine a key value store with a single server, this could be something simple like level DB. You do a get and you get the thing. You do a set and it sets. That's it. There's no argument there. It just happens. So what do you get? You get, well, it's going to be relatively fast because there's no clustering, there's no network lag or anything like that. It's probably direct connection between your application server and the database server, and that's it. Scaling is going to be hard because in this case, we're assuming that it's a database that doesn't scale, but you could create your own manual sharding perhaps on the application level. So the impact there is really at the very basic level that you can't do a great deal. You get the speed that you get from key value store, but you don't get much else. You don't get much in the way of query. You don't get much in the way of scale. Then we then look at a master slave document database. Doing a get, well, you come in from, you pull in that get from one of the slaves, you do a set, and then it takes a while to propagate out. So again, the impact there of the architecture is that we have eventual consistency. We also have the possibility of the master being a single point of failure. So scale is perhaps more difficult to achieve. But it should be relatively fast because documents are quick to write and quick to read. The query might be a bit slower depending on how it's achieved. But you have these, like I say, aggregates of data. Thanks. So it should be relatively quick. But it's going to be harder to scale with that topology. And then you might have something like a Dynamo-like distributed master store. In this case, something like Cassandra. So you do your write in, it distributes it out. And then you could write into that same document in another place or in a different document into another server, and you want to update it, but your SDK, your client, has chosen some other server to write into. So and then what I was trying to show in the animation here is that you can have a situation where before it's had a chance to replicate out, one of the other servers could disappear, and then that gives you a conflict. So when you come to read it, the column store will look for, it'll come back with 2 or 3 of copies of this data from different servers, and it will say, well, I've got a conflict here, you need to fix that. So the impact there is that really, the data model is going to favor favor writes. So it's, like I said, with the column store, it's very fast to append new columns, but actually the architecture favors reads because writes become a little bit costly when you're having to go back and check whether those writes have been stored consistently across several servers. Whereas when you do the reads, you're actually probably just going to say, well, give me 2 out of 3 and that's okay. So that gives you faster reads. So the architecture and the data model kind of fight against each other a little bit there. Query, like I say, data model allows for really good range queries. The architecture brings in this eventual consistency problem. And scaling, well, the architecture is perfect for scaling. And then a similar one would be a document store like Couchbase running with a distributed master. So there you have this situation of you write in, there's a single master to write into and read out of, but again, it gets replicated. And then when you come to a read, you're reading from where you wrote it, so you'll have the same data back that you wrote. But in the instance of a failure, you make this trade-off, like I say, that you're happy to lose some write availability or possibly even read availability for a few seconds while the cluster ensures that you're not going to end up with a split brain situation and end up with 2 different copies, divergent copies of the data. So then what it'll do is it'll promote one of the replicas and then give you that as the active copy, but there's a little delay there because we're preserving consistency over availability. And then it'll update things on the map of how the cluster looks, and then you'll start using that version of the data instead. So the impact of that is that you have this on the data model, simple because it's a document, so your gets and sets should be fast, but the architecture as well is relatively fast for for reads, and then for writes as well. So long as you don't have a single document that acts as a hotspot, then you can just carry on adding nodes to distribute the load across the cluster. For the data model, you query is a world of innovation right now. So there's things like Nickel from Couchbase, or you have MongoDB's query, you have the JSONic project, where there are all sorts of different ways of querying JSON. On the architecture side, you have this strong consistency, so that makes it fairly easy to query data and know that what you're getting back is what you expect to get back. And for scale, again, data documents are easy to distribute, and the architecture makes it linearly scalable. So just as a kind of a recap, the impact for speed in NoSQL is really that the data model, the simpler the data model, the faster you'll be. On the architecture side, once you go beyond one server, you need to basically avoid the master-slave situation because you'll be slowing yourself down on writes in a master-slave. For scale, again, distinct aggregates of data like key-value pairs or documents are easy to distribute. And architecture-wise, again, a master-master topology allows you to just rack up more servers when you need them and then redistribute the data across the newly enlarged cluster. So next steps, if you're interested in Couchbase, so Couchbase is a distributed document store, then you can come and look at our developer portal, developer.couchbase.com. We've got forums, there's free online training, all that kind of thing. And I think that's my time up. So thank you very much. I'll be on the Couchbase booth if you want to come and win a GoPro. Thanks a lot.